All right, I think we can get started. My name is Chris Dustin. I'm the director of the Mendel Observatory at Merrimack campus. As many of you know, we like to host every Wednesday night an open observing session in coordination with the North Shore Amateur Astronomy Club, who do the main workhorse working of the event while we just open the telescope and let them in. We like to have the public come up here and be able to observe all the interesting objects that are out in the night sky at any given time. But of course, the pandemic has gotten in the way and has changed that completely. So starting when the pandemic happened, we started thinking of ideas we could do to keep you guys engaged in what's going on in the observatory. And so this is the first thing we sort of thought of, is try to have some kind of live stream event. So I'm sort of testing the equipment a little bit. I'm doing it on Wednesday night to try to see if there's any interest. But if people don't want to watch or want to watch, it's okay. My plan for tonight is to definitely check out the 3 planets, Jupiter, Saturn, and Mars. A couple of dimmer objects I want to try with with our new astronomical camera, the Ring Nebula, maybe a couple of other bright planetaries. At the moment, what we are looking at is Jupiter, and you can see the image is not that great. You can, if you look at it and we get sort of lucky seeing, you can occasionally pick out some cloud bands. But what's happening now is that the telescope is pointed very, very near the horizon. So Jupiter is very low in the horizon. I would estimate at about 25 or 30 degrees off the horizon. And when you're looking through a lot of atmosphere like that, basically the air scatters the light from the planet, makes it bounce around like that, and makes it fuzzy. And so that's partly what you're seeing now looking at Jupiter. Now I can just barely see a couple of dark red cloud bands going through the planet of Jupiter there, but they're pretty tough to see. I'm going to play with the settings a little bit in a second, and we'll see if we can get a better image. So let me just talk a little bit about what is going on here. It's other things that are causing the image that you're seeing. You can see the image is also bouncing around quite a bit. So partly that is due to turbulence in the atmosphere. Like I said, we're looking through quite a lot of atmosphere, so the turbulence causes the image to bounce around. In addition, the Merrimack Observatory is sitting on top of a giant building. That building has all kinds of various vibrations and mechanical things happening in it. It's an engineering building. There's an HVAC system. In addition to all that, we had a small water leak the other day, and so there's additional fans blowing in the building to try to dry off the water. And so partly what's happening is you're looking through a lot of atmosphere, and partly what's happening is you are sitting on top of a building, and so that is not a great way to do astronomy, and you're seeing some of the effect of that. So the first thing I'm going to try to do is to try to get the cloud bands to appear a little bit better, and then I'll talk a little bit about what the cloud bands are on the planet Jupiter. Fortunately, I can't get the image much better than that. Like I said, we're looking through quite a bit of atmosphere. But you can, on occasion, at least with my eyes, I can see some horizontal bands going sort of from the lower left to the upper right of the planet. So let me just talk a little bit about Jupiter while we're here. We might as well talk a little bit about the planet. So it's the most massive planet in the solar system. It's a gas giant. That means that it's got a presumably rocky or liquid core, but it's made of various states of hydrogen as you move out from the core, probably a liquid layer, then a gas layer, and it also has an atmosphere. And the cloud bands that you see are because of the atmosphere. Jupiter has an extreme atmospheric behavior because it's one of the reasons is because it's rotating so quickly. Completes one rotation in about 10 hours. Given that the planet is about 10 times the size of Earth, that leads to some pretty extreme weather behavior. You've probably seen pictures of the Great Red Spot on Jupiter. That's a storm. It's a long-lived storm. It's been going for like 400 years. This is very unlike storms on Earth, which die out after a few days to a few weeks. And so there's a pretty incredible storm-like activity on Jupiter. Actually, the cloud bands on Jupiter actually go in different directions. So fortunately, you can't really see them tonight, but the dark bands are going in one direction, and the that way, I guess, that way is from your perspective, and the white bands are going like this, and they're actually moving in opposite directions. That's an extreme example of the Coriolis force, which creates storms on Earth. So like I said, I don't think I can get a much better image of Jupiter now. Perhaps when you saw me messing around with the settings, you saw a couple of little white dots appearing off to the upper right of this image. Those are actually Jupiter's moons. And so the next thing I think I'd like to do is try to get some settings to play around a little bit and see if I can get the moons to pop out a little bit better, and then we can talk a little bit about them. Yeah, so that's actually pretty cool. So in this image, you can see three of Jupiter's moons, one of which is right next to the planet, right in front of it or right behind it. So, sorry, I should say what I did is I increased the exposure, so now Jupiter is completely washed out, but we're picking up the fainter moons. With your eyes, if you looked through nearly any telescope at Jupiter, you can very clearly pick out four moons. Those four moons are the four Galilean moons that Galileo discovered when he looked through Jupiter for the first time through a telescope. And also the discovery of the Galilean moons was the idea that there are moons going around other planets, and that sort of threw a crutch into the idea of a geocentric solar system where everything went around the Earth, because if you could have things going around other planets, then presumably you could have things going around the sun or things going around other planets, and so that sort of put the last nail, or one of the last nails, into the geocentric model of the universe. Now, I can't tell you which exact moons those are. There's various, you can go on the internet and see what the current state of Jupiter's moons are, and they will tell you what they are. My guess is that one that's really close to Jupiter is Io. Io is an extremely volcanic moon. It's not lava that comes out of the volcanoes on Io, but sulfur. Of course, sulfur comes out of the volcanoes on Earth too. So it's just an extreme version of that, where nearly 100% of the gas that's outgassed by Io is sulfur dioxide specifically. So Voyager saw that as it was traveling past Jupiter, checked out Io, saw a crazy volcanic surface with old and new lava flows all over, including some active volcanoes. And now we've been back to Jupiter with the Galileo spacecraft and seen the same thing. Io is heated by how close it is to Jupiter. So the tidal forces on Io are so extreme. They're what's actually sort of melting and heating the inside and creating that volcanic activity. The other moons of Jupiter, the other Galilean moons, are Europa, Ganymede, and Callisto. I can't be totally sure which ones are which. And even the one I'm guessing is Io could be one of the other moons, because they orbit in a plane which is aligned with our eyes. And so at any given moment, any moon could be nearby Jupiter. It's just a pretty good guess that that one is Io. So I'm going to try to scan the telescope around a little bit and see if I can see the other moon. I know it looks like I don't have any idea what I'm doing, but the directionality of the camera is random every time, so it's not so easy to just push left or right on the camera and make it go in the right direction. Okay, that's pretty far. I would say that the other moon is not going to be found, which probably means that it is also behind Jupiter. Let me go a little bit further on the other side. I don't want to lose Jupiter because our telescope has had some alignment problems. So I don't want it to totally, and I actually totally have, so I'm going to have to get it back on Jupiter. Let me take one more crack at that. Oh, I don't see any other moon, so I guess we should think that the other moon is behind Jupiter. Okay, so, and of course, if anybody has any comments or any questions, feel free to drop them in the chat. I've never done this on YouTube before, so I don't quite know what I'm doing, but I think I can see what you are going to say. So please, if you have a question or want to say something, please just drop it in the chat, and I will do my best to answer. I think I'm going to spend a few more minutes playing around with Jupiter before going on to Saturn. The transition between Jupiter and Saturn might take a little while, because of the way the telescope works. Oh, actually, no, it should be right there. So you can see in the sky, what I really should have is I should have a second camera that I can point out at the sky. You can see in the sky that Jupiter and Saturn are two of the brightest objects, and they're right near each other, and so it will not be hard to go between them. So I will do that momentarily, but I'd like to play a little around with a little bit, trying to take another crack at getting Jupiter's cloud bands to look nicer. So that actually might be the best. The image is not great, but now you can sort of see the cloud bands. I see two of them running from lower left to upper right. It doesn't seem like it's going to get any better for us tonight. Once it gets a little bit darker, I can try again, but once it gets darker, Jupiter is going to be a little bit lower in the sky, and that might be a little bit more difficult. Just give me a few minutes to take a screenshot of this to save for our records. And I think I just want to do the overexposed one too, so I can see the moons. Okay, great. So now I think that I will slew over to Saturn. I see somebody's asking, can we look at Saturn? So that is what I'm going to do now. That same person is also interested in seeing Jupiter's surface. So Jupiter does not really have a surface. The best thing that I can show you is Jupiter's cloud barrier. Cloud level layer, right? So Jupiter is a gas giant, and so its surface is actually a sort of combination of gas and liquid, where there's sort of a transition from the core outwards between gas and liquid, and then there's a real cloud atmosphere. So Jupiter does not really have a surface in the traditional sense. This is the best thing I can show you that gets close to Jupiter's surface. The same thing is true of Saturn, and let's go and check that out. Oh, it's right there. Great. So one of the mechanical things that's happening here, let me just talk a little bit about the Mendel dome before I go on to showing you, try to get the better image of Saturn, is that, so the telescope is surrounded by a dome and there's a slit that's open now to the outside. And so when I move to a different object, if the telescope moves too far away from the slit, I have to rotate the entire dome. It's quite a dramatic experience. But because Jupiter and Saturn are so close in the sky, it is quite easy to just pick them out like this. I see the person who's asking about Jupiter's surface is saying about the cloud bands. I was talking with I did the best job I could to give you pictures of the cloud bands. We're looking through so much atmosphere that it's really fun. And also the seeing is not great tonight, and so I could not pick up any of the atmosphere. You drove the dome? Awesome, fantastic. Yeah, so it's just not a great night to look for Jupiter's atmosphere, unfortunately. It's too low in the sky and too jumpy. I can use the camera to stack images, but it's jumping around too much for me to really be able to even stack it, so it's just not a great night. I might try when it gets darker. So let me play around with Saturn here. I mean, without any adjustment whatsoever, you can clearly see that there are rings, and there's a nice separation between the planet and the rings itself. Let me see if I can get a slightly better exposure time. I don't know, it's hard to tell, so just to tell you what I'm doing now, this number that I'm changing is the number of exposures to combine at one time. So the exposures, typically in astronomy what you do is you take very long exposures so you can get down to the very details that you want to look at, like the planetary surfaces, the cloud bands, some finer details of some astronomical objects or whatever. Here, this camera only takes very short exposures and then shows them live, or you can stack them on top of each other. So what I was trying to do is stack many images on top of each other. That's what this number is. So this is one image, and this is two, and I can go all the way up to 6. What happens at higher numbers is you get this grainy, like it's trying to stack, but it's not sure what it's doing. You can actually see a circle that goes around the cloud bands. That might, it goes around the ring. That might be a real thing. It's kind of hard to tell, though. So I think the stacking is not good for planets. It looks like the stacking is really should be set to about 1. And let me just get rid of these things, and I'll just tell you a little bit about Saturn. So actually what's cool about this image is you can sort of see that the ring goes around the top part of Saturn and behind it in the back. So we're kind of looking at Saturn from below. So Saturn's obviously a little bit above in its ecliptic. And if I knew the relative orientations of Saturn's rings, I could tell you whether it was summer or winter. in different parts of Saturn. I think what we can say right now is if this image is right side up, it's summer in the southern hemisphere of Saturn, but I don't know if it's right side up. If it's not, it might be summer in the northern hemisphere, right? So anyway, so Saturn is the next largest planet in the solar system. It's another gas giant like Jupiter. It's a little bit smaller than Jupiter in both mass and size, but what's interesting about Saturn is it's actually so low density, meaning that its mass per unit volume is so low that it actually would float in water. So a very popular thing we talk about in astronomy is if you had a big giant bathtub, you could get Saturn to float in it, which I don't know how you would do that, but that's the story we tell. So it's a gas giant just like Jupiter. It doesn't have a solid surface per se. Presumably there's some kind of rock or iron core, but the inside is basically a transition of various hydrogen elements and hydrogen states of matter. There's a liquid or a metallic hydrogen layer, then a liquid hydrogen layer, then a gas hydrogen layer, and then it also has clouds. I don't think I've ever seen the cloud bands on Saturn with our telescope. It does have cloud bands. They're not as pronounced as on Jupiter. Presumably that's because it's cold, so there's probably ice in the atmosphere. It's further away than Jupiter, so there's probably ice in the atmosphere, which makes the surface of Saturn, the cloud bands of Saturn, more hazy. The bathtub would have so much mass it would eat Saturn. I don't know about eat, but it certainly would sit there and float. It's funny, I'm getting some unusual connections, like the connection appears to be dropping and coming back. I don't know if that's something that you guys can see or not. I've never been up here. Maybe there's a bad internet connection or something. I'm just going to plunge forwards. This is all part of the experiment. So anyway, a key characteristic of Saturn is that it has rings, obviously. In fact, Saturn is not the only gas giant to have rings. All four gas giants, Jupiter, Saturn, Uranus, and Neptune, all have rings. Saturn is the only one we can really see from Earth. Now, the Hubble Space Telescope can, I think, see all sets of rings. We didn't know the other three gas giants had rings until we sent Voyager 1 and 2 out there, and they detected all the rings. But the rings on the other gas giant planets are much fainter than Saturn, which is clearly very, very obvious. From antiquity, we knew that there was, people called them like the ears of Saturn and things like that, whereas now, and even with our very shaky image here, you can tell that there are indeed rings there. The rings are formed as part of the formation process of the planets as the gas condensed out of the solar nebula and created these gaseous planets. Accretion disks formed around them as their gravitational potentials got large enough to sort of grab whatever rocks and debris that was around. And this rocks and debris, sometimes they were large and became moons, or crashed together to become other moons, or split apart to become small particles. The rings are essentially a bunch of small particles which range from sort of centimeter or smaller sized to like car-sized, boulder-sized. They're mostly ice, which is why we can see them. They're very reflective. So the rings of Saturn are not like solid disks. They are that you could like ride on or something. They're very narrow. I think like 10 meters wide, so 30 feet wide is what I've heard. My understanding of how narrow Saturn's disks are. So that's pretty amazing. The fact that we can see something that's so narrow. I mean, it's very large, but it's a very narrow band. So that's pretty incredible to me. So they're mostly ice. The thing about Saturn's rings and all the rings of the gas giant planets is they're ephemeral. They are not permanent. They are raining onto the surface of Saturn as we speak. Every year, more and more dust rains down from the rings onto the planet. Also, sometimes the rings get disrupted by moons passing through them. These are called shepherd moons. They are sometimes disrupting the rings. In some ways, they are also keeping the rings stable. And actually, those are the moons that replenish the rings. So although the rings are sort of decaying into the planet, they're continuously getting replenished by the collision of all sorts of little moonlets around Saturn. And of the rings themselves. Saturn has a large number of moons. It has the most number of moons in the solar system, 82, I think, at last count. Jupiter has 79, I believe, and so there's just lots of rings in those, lots of moons in those systems. As we saw on Jupiter, we could see 4 Galilean moons. You can often see moons around Saturn. I'm going to have to do the same thing I did for Jupiter and turn up the brightness, turn up the exposure time to try to reveal those moons. Unfortunately, I don't know that much about the moons. I mean, I can talk about Titan, which is one of the most fascinating moons in the solar system, but I'm actually not sure if what we're looking at is Titan. So let me first change the exposure time and see what we can see. Okay, so you can see now that there is a dot forming in the frame. And so I'm going to scroll around a little bit and make sure that I believe that, let's see, there's another dot over there, there's some other dots. So actually my understanding is these are the moons of Saturn, and that one that's furthest out is Titan. Now I cannot name these, and I guess I should be a little careful because I'm actually not completely sure that these are the moons of Saturn. They could just be background stars, but my understanding is that these are the moons. You can see one there. You can see a couple other dots in the image. I can see two below Saturn, one off to the left and one above it. Saturn has a lot of moons, and I think these are them. So let's talk a little bit about Titan, because that's a super interesting place. So I think that moon right there in the corner, come on, is Titan. So Titan is one of the only moons, is the only moon in the solar system that has a substantial atmosphere. There are other moons that have very, very thin atmospheres, like Triton around Neptune. But Titan is the only one that has a substantial atmosphere, and it is quite substantial. When you look at it, when Voyager first looked at it, it obviously was a cloud-covered moon with no obvious surface features besides the clouds. So we were obviously very interested in getting to Titan, because if you have clouds, you could maybe have liquid water, and liquid water is the telltale sign that there could be life there. So we sent a probe to Titan specifically with the Cassini spacecraft, which visited Saturn in the early 2000s-ish. It was a probe called Huygens, named after a physicist who studied light. So Huygens was a probe that crashed through the atmosphere of Titan to the surface, landed on the surface, and studied the planet. It's a pretty dense atmosphere, dense and hazy. The surface is basically, sort of Mars-like, with the exception of these large methane or ethane lakes that are on Titan. So Titan is a world of atmosphere and liquid, but the liquid is not water, the liquid is methane. So it's a totally crazy place where there's just craters and mountains and these giant lakes of methane. So there's no life living there in the way that we understand life, because we don't know of any life that can survive in a completely methane-based environment. But of course, you're probably aware, humans and other life forms on Earth are based on carbon, and so any of the other molecules that are like carbon, including things like silicon, things like oxygen, could maybe be the basis for life, and something like methane would have to be like a hydrogen-based life form, I suppose. But in any case, the idea is that, or nitrogen. I'm not sure. But yeah, indeed, it would be. There could be life on Titan because there is liquid there, but it would be life totally unlike our own, with totally different chemical processes. So Huygens basically told us there's no large-scale life, but it just made us more and more interested in going and checking out Titan. And so yeah, Exxon Valdez would love the moon, because there's methane and ethane everywhere, I guess. Okay, so I think that I'm about ready to move around off of Saturn. After I take a couple more screenshots just for our own records. It's too bad that I can't get a better image for you guys. I think I can't do much about it in terms of where the planets are situated tonight, very low on the horizon. But even if they were higher, I'm not sure, based on where I am on top of a building, whether the image would be much better. It's really nothing like being in the dome and actually using the telescope to observe these planets with your own eyes. So I'm just going to quickly get it refocused here. All right, so those are the two planets, Jupiter and Saturn. On the list of things that I want to look at tonight, I definitely want to check out the Ring Nebula, because I believe that we should be able to see some really nice colors in it. I also really want to check out Mars, because I'm going to be wanting to look at Mars during the event, which I'm doing next week. Next Wednesday, we're actually doing a big Observe the Moon event where I will be doing this, looking at the moon. The moon is similarly very dramatic. Unfortunately, the moon is going to be very near Jupiter and Saturn, very low on the horizon. I'm going to have a lot of the same problems I'm having tonight, but that is happening. So tune in. I'll probably put it on YouTube in the same way that we're doing now. So since I've got a theme of planets going on, let's just bounce over to Mars before I start checking out some of the more extreme objects like the Ring Nebula. So this is just going to take a moment. I'm going to have to monitor the telescope while we slew over to Mars. And actually, let me just tell you what I'm going to do technically. So the field of view on the camera is quite small, and our telescope is reasonably good at finding things by itself, but not perfect. And so sometimes it can be a little bit off, and if it's a little bit off, I'm like completely lost in the sky because this little tiny screen is all I have to look at. So one thing what I'm going to do is I'm going to find a star that I can actually identify, tell the telescope where that star is, and that's going to help me slew over to Mars. At least that's the principle. So first I'm going to find a random star, which I know is quite bright. Let's do Altair. So I am going to slew to the star Altair. With any luck, it will just automatically be in the screen when I do this. Oh, look at that. Perfect. So maybe I don't need to do any corrections at all. You can see Altair is a very bright star. It's overexposed to the center. That's why there's that black dot there. Cool. Well, I think I'm kind of optimistic, so I'm just going to go try to slew to Mars. This will take a few minutes because the telescope needs to essentially completely rotate all the way around. You can see it moving in the background, so enjoy that, I guess. Yeah. It's funny, Mars was not actually very far away from Jupiter and Saturn, but because of the way the telescope worked, it had to go all the way around. So I am now going to spin the dome. I assume you're just going to hear like a super loud grinding noise. I'll mute myself so you don't. Well, there it is. Maybe that's not bad. Well, I don't see Mars. I think I need to go a little further. There it is. So the accuracy was good, not great. But at least good enough so I could find it. Okay, here's Mars. Let me play with the exposure times a little bit. I have not looked at Mars yet, so I kind of have no idea what I'm doing. Okay, let's talk a little bit. So I have to say, I'm not exactly sure what I'm looking at. I'm sort of fascinated by this. There is definitely a dark spot on the surface, and so, mostly when you're looking at Mars, what you want to look out for. Sorry, I'll get the words away. Normally what you want to look for on Mars, if you're an observer and you want to get a good view of Mars, is can I see the polar ice caps? Because Mars has these frozen carbon dioxide ice caps. What I'm seeing is a stripe on the lower part of the Martian surface. I think I'm going to tentatively not try to guess what that is. There are storms on Mars, pretty extreme dust storms, and it's possible that we're looking at something like that. I do not want to try to guess. Does anybody who might be a better observer, more familiar with the structure of Mars, as you can see from the Earth, want to tell me anything about what I'm actually looking at? This is kind of embarrassing. I've never seen Mars with such a device, so I actually don't really know what I'm looking at. Pretty interesting. Well, so I guess I'll talk a little bit about Mars while we're here. So Mars is the fourth terrestrial planet, Mercury, Venus, Earth, Mars, and then there's the asteroid belt and Jupiter. So Mars is closer to us than Jupiter, but Mars is a very small, rocky planet, half the size of Earth or less. Also very low mass. Mars is essentially a sort of dead red planet, where the red in the Martian soil is mostly due to oxidation with oxygen. So it's basically like what happens to iron when it rusts. There are several reasons why Mars looks the way it does. Just seeing what the comments are. Oh, great. Fantastic. Saw all these planets through Orion star was 4.5 inch. And also people are looking at Mars outside. Awesome. So you can go outside and observe all three of these planets. Mars is sort of off to the east-southeast, and Jupiter and Saturn are towards the further south than that. And of course, like Mars is near one of its closest approaches to Earth that it's going to have in the next several years. I don't know, some large number of years, 10 years, 12 years. So it's very, very bright and very, very close. I'm going to take a couple screenshots of this thing so I can try to figure out what that cloud band actually, what that dark band actually is. So anyway, so Mars has had a very interesting history as a planet. So it's a rocky planet, so it formed close to the sun, and it's basically its location now. It condensed the heavier materials like rocks and iron condensed out of the solar nebula, where gas couldn't form. So close to the sun, it was too hot for gas to condense out of the solar nebula. Only rock and sort of metals were able to do that, and so that's how the terrestrial planets formed. Now, Mars formed with a pretty small mass, and so essentially, although there was a Martian atmosphere some number of billions of years ago, the planet was so small that it couldn't hold on to the atmosphere. It did not have enough gravitational force to hold on to the atmosphere. In addition, it has a very small magnetic field, almost non-existent, not really a global magnetic field. And so the solar wind was able to strip away a lot of the atmosphere as well. But Mars did have an atmosphere long enough for liquid water to run on Mars at some point in the past. You can pull up images on the internet of channels through Mars that are very obviously dry riverbeds. We now have sent probes to Mars that have driven around in these dry riverbeds at the bottom of craters and seen things that look identical to the dry riverbeds on Earth. And so we infer that Mars was essentially a very wet and warm place. Some number of billions of years ago, probably between 3 and 2.5 billion years ago, Mars essentially dried up, and we think that that's sort of when the effects started taking over. It was able to hold onto its atmosphere for a while, but not very long. The magnetic field wasn't able to protect the Martian surface, and the solar wind essentially was able to blow the atmosphere of Mars away. And so now there is an atmosphere on Mars. It's mostly carbon dioxide. It's extremely thin, very, very thin. Totally unlike what we have on Earth. I guess on the topic of the thin Martian atmosphere, one of the interesting things that people are thinking about sending to Mars now are drones. And in fact, NASA is going to send a drone to Mars. In fact, I think it launched last month, right? So it's sending a drone to Mars, which is going to fly around in the Martian atmosphere. And I really recommend, I sent a video out to my students the other day about this, I really recommend anybody go and check out Veritasium's YouTube video about this. So Veritasium is a YouTuber who does great science, great physics videos. He went to the lab where they're developing this probe and talked to the engineers who are developing it. And it's really interesting trying to construct a drone that flies in a very, very thin atmosphere. It's very, very difficult. And so they have this thing running, and the blades have to turn so quickly. There's two of them on top of each other because one of them is not enough, so you want to have one that pushes more air onto the second blade, so the second blade sort of enhances its effect, and then you can get this thing to fly around. And so this drone is going to launch, sit on the Martian surface for a day, get a day of charge, and then it has every day it gets about 90 seconds of flight time charged from the sun, right? Mars is quite a bit further away from the sun than the Earth is. The sunlight there is much weaker, and so you're going to charge the solar batteries much slower. So after a day of charge, this thing gets 90 seconds of flight, right? So it just takes off, flies for 90 seconds, however far it can go, lands, waits a day. NASA tells it to fly somewhere else, and it's going to fly somewhere else. So this is a super interesting experiment that I'm really anxious to hear about what goes on the Martian surface when it reaches there in, I think, early 2022 or something like that. Okay, what else can I say about Mars before moving on? Mars has a couple of satellites. They're very small. Deimos and Phoebe is, I think, what the two Martian satellites are called. They're very small. They're essentially not really even moon-like. Our moon is circular because it's quite large. Deimos and Phoebe are not circular. They're just kind of lumpy rocks. So they haven't grown large enough to circularize under gravity. Let's see, what else about Mars? Guess that's kind of it. For a while in the early 2000s, the Martian surface was mapped better than the Earth's surface because we had sent our best detectors up to Mars without bothering to send global surveyors out into space around Earth. So for a couple of years, we had better maps of Mars than of the Earth's surface. Now, of course, we have GPS satellites everywhere. That's not true anymore. But that was true for a little while. I'm definitely interested in this dark cloud pattern we're seeing. I guess I'm going to say that it's probably a dust storm, not having much experience looking at Mars from this perspective. I was expecting to see some white ice caps, which I don't necessarily see. I guess I could kind of squint and see one off to the lower right, but I think that's probably just me being hopeful. So I think that's all I got to say about Mars. Anybody have any particular questions before I decide to go check out something a little bit more exotic? All right, not seeing anything. What I want to try to check out now is the Ring Nebula. So this is basically pointed directly upwards in the sky, and so I'm going to need to slew the telescope up there. Say goodbye to Mars. Actually, correction, I'm going to do something a little bit different. On account of the fact that I'm not completely convinced about the alignment of the telescope, although I found Mars fine, I'm going to point it at an extremely bright star in the sky, Vega, which is almost pointed directly upwards from us because that's very near the Ring Nebula. So I'm going to point it at Vega, make sure the telescope is aligned, and then jump from there to the Ring Nebula. Interesting. I suppose that I am supposed to consider that to be Vega. Vega is extremely bright. I was expecting something a little bit more washed out. If you'll excuse me, I'm going to have to do a couple of optical verifications that we're actually looking at Vega. So just give me a moment or two. Yeah, I'm not sure that's Vega. I'm going to spin the dome. So, loud noise coming. All right, I guess I am convinced that that is Vega. Just a little unexpected playing with the camera and knowing what to think about the objects that I'm looking at, because I'm not used to thinking about them in this like highly exposed kind of form. So let's try to find the ring now, because we should be very close. I'm going to have to play with the exposures a little bit, so just give me a few moments. Okay, so indeed, I am looking at the Ring Nebula. You can just see a star near the center of the sort of lower part of the image, and the ring is off to the upper right. So I am going to try to get a better image. I know what I'm looking at, and you guys probably don't, so just let me play around a little bit. You can start to see some color, so I'm starting to get a little optimistic about what this is going to look like. All right. All right, so you can see a circular ring-like structure at the center of this image, and I am very excited about this. So let me try to tell you what's going on here. So this is the kind of image that you really don't get by looking at these objects with your naked eyes. So our eyes are just not sensitive enough, no matter the size of the telescope. You are never essentially going to see any colors in any objects. Now, that's not entirely true. I've heard that things like the Orion Nebula through incredibly giant telescopes can show you this kind of images, but really you need a camera to get color images. And so that's what I'm doing here, is I'm using a camera, and it's stacking up a bunch of images of a different exposure. In this case, I think the exposure is about 2 seconds long, and it's being stacked 6 times. Now, you can play with these kind of camera settings to get all kinds of different effects and all kinds of different things. It's a little upsetting that the stars are so fuzzy. Maybe I could play around with the focus a little bit to try to get better stars, and so I'll do that after I talk a little bit more about what this object is. Yeah, as Justin says, it looks like the Helix Nebula. The Helix Nebula is another planetary nebula, a similar kind of structure. So planetary nebulas, although they have the word planetary in them, are not planets. They were named planetary nebulas because when people first looked at them, they thought they were planets. They are sort of large and fuzzy. And you can see the ring. When you look at the ring with your naked eye, it doesn't look that large. It's relatively small. But in this image, it's kind of the size of like Jupiter and kind of a little bigger than Mars that we were looking at, right? So that's how it got the name Planetary Nebula. Really, planetary nebulas are dead stars. So when stars that are about the size of the sun or a little bit bigger, up to like maybe 8 solar masses, 10 solar masses, when they die, they don't die in this explosive destructive way that we often imagine stars dying, those are called supernovae, right? These kind of stars die slowly. They shrink, and they maybe burn a little bit of helium along with burning hydrogen, and then they sort of expand, and they sort of shrink, and then they expand, and eventually the energy produced in the center spikes and sort of puffs out the star, which can't be held on by gravitational force anymore, and just sort of continues to expand, leaving a hot core called a white dwarf. And so this is actually what that is. You can see the colors, the ring structure around the outside, the sort of red on the outside and green on the inside. That's this expanding shell expanding around the dead white dwarf in the center. Now we may be, and actually I can almost see in the center, we might be able to see the white dwarf. So I know that the Ring Nebula has one of the few white dwarfs that you can actually see with telescopes, traditional sort of amateur type telescopes. I might be able to see that. I'm not sure. Maybe I'm just tricking myself. But the idea is that what we're looking at here is a glowing cloud of expanding gas. Actually, planetary nebulas, most of their light comes out in the oxygen line. People are trying to volunteer Justin to come help. Yeah, Justin, you can come help. Of course, I can't let you on campus because no one's allowed on campus, right? Yeah, so planetary nebulas are mostly glowing in oxygen. They have a few other elements in them, but mostly it's the residual oxygen, the first ionized or second ionized oxygen line, can't remember, that is giving it this characteristic color. There's probably also hydrogen in these things that's left over from the star formation. That might be the red that's around the very outside. So I'm going to spend a few moments trying to get the thing in focus, which is going to be, looking at the stars and trying to get the stars in focus, and I'll come back once I start to play around a little bit. Yeah, unfortunately, it looks like the star images are the star images. I'm probably not going to be able to get it more in focus than it is now. Yeah, unfortunately, it looks like I'm not going to do much better than we did before. It's just in focus. It's just pointed straight up. There could be additional vibrations. If I showed you the instrument that I'm using, there's a bunch of cords hanging off of it, which is probably causing some extra vibrations and making it difficult for the computer to do this stacking. Okay, so I see we've got a lot of suggestions for stuff to look at. M33, which is a face-on dim but large galaxy in I think in Andromeda or Triangulum. M13 is a globular cluster. I think M13 is too low tonight. Edicas, isn't that just a main sequence star of some kind? M13 already. Dumbbell Nebula, great one. Uranus, I don't know that Uranus is up. We'll do Uranus if it's up, definitely. 15, 31, 31 is the Andromeda Galaxy. So these galaxies, M31, they're very large, and same with M33 is very large. And so I'd like to check out a galaxy, but I don't know that those large galaxies are going to be useful in this small image scale, and also the fact that they're pretty dim when spread out. So they're bright as a whole, but relatively dim, sort of per unit area on the sky. So let's take some of Justin's suggestions, maybe. Yeah, so let's try M13, because indeed M13 looks like it is high enough up off the horizon, and it's like relatively close to where I am now, so I can do my sort of star hopping around a little bit. So first let me jump to Vega again. M13 I don't think is going to be a great image, but I think it will be interesting to look at. Yeah, that's what Vega looks like if it's massively overexposed. Let's fix that. And I'm just going to do a quick alignment to make sure Vega is as close to the center of the image as I can get it. Telling the telescope what it is actually looking at. Okay, now M13 is quite bright. It's a globular cluster, and so it should be pretty obvious when it shows up on the screen. Looks like we're going below the slit, so I'm going to have to rotate the slit. So loud noise. Just going to do a visual check. Oh, it's not there yet. Wow. Wonder if that's what M13 looks like through a system like this. I'd like to try a few more adjustments before I settle on something that looks good. Well, never having looked at M13 through our video camera, I suppose that this is a reasonably good image. You can see the stacking is not working perfectly because every so often it sort of jitters. Maybe it's better without the stacking. Or maybe it is not better without the stacking. Yeah, I'll talk a little bit about what M13 is. Let me just try it one more time to get a better image. All right, let's go with that. It's not the greatest thing, so we'll just talk about this. I mean, yeah, Justin, the stacking reduces noise, but because the telescope is so jittery, I think it's having trouble lining the stars up, and there's quite a lot of stars in something like M13. So M13 is a globular cluster. So this is a group of stars that were all born about at the same time together. I mean, if you started counting, you would end up with hundreds of thousands of stars in there, likely. Globular clusters are very dense, so there's a lot of stars in globular clusters. As opposed to open clusters, which are typically fewer. The other difference between globular clusters and open clusters is that globular clusters are very old, at least 10 billion years old, often older. So these are very old, generally low-mass stars that have been just churning away, burning hydrogen into helium over their entire lifespan. There are various kinds of planetary nebula and solar deaths and things that happen in globular clusters, but generally they're just very old stars where all the young blue stars have already gone supernova, and what is left over are the remnants. And as globular clusters age, the stars sort of sink towards the center, so they get this higher concentration in the center, and you can often age globular clusters by how dense their center is. There's not a lot of colors in this image. You might be able to pick out some sort of red-hued stars. Generally, globular clusters are basically red stars, old red stars. Globulars also orbit the Milky Way in an unusual way. Basically, nearly everything in the Milky Way is in a disk, right? The center is here. There's a disk that's out here. The sun is at some location, maybe 2/3 of the way out. Most of the stars of the gas and dust of the Milky Way are in this disk. Globular clusters are actually situated in a sphere around the Milky Way, in this cloud of globulars, because they formed essentially before the disk was able to form. And so they formed while the galaxy was still kind of this spherical object, and the orbits are sort of, instead of orbiting in this nice disk, the orbits are sort of randomly randomized everywhere. I think, what else can I say about globular clusters? Astronomers like to study merging stars in globular clusters because the expectation is that they are so dense that there will be a lot of mergers in these kind of globular clusters between old red main sequence stars. There's also ideas about black holes being quite prevalent in these kinds of objects because the constant mergers of stars tend to create more and more massive objects, which either, if they start as a black hole and swallow stars, they get to be bigger black holes. When stars merge, they can become another star that can go supernova quicker because it's more massive, and so astronomers like to look for black holes in these clusters. Okay, So, what should we look at now? So I guess I want to vote that clusters are kind of okay. Should probably use a little bit of tweaking on my part. I should try to get a good screenshot. Yeah, the stacking, that's what all that noise is around the stars, is the stacking is not quite lining up on each other because the atmosphere is shaky and the telescope is shaky and that kind of thing. Justin's giving me more suggestions. So, double cluster is a fantastic object, but it's really more like a binocular object. The double cluster is very large on the sky, and so this image would basically pick up nothing. It just would kind of look like the image we have now. The double cluster is just too big of an object. The screen size we're looking at is just too small. I will find out. Great. What's Colinder 399? I'm intrigued. Justin Long. Coat hanger cluster was not found, and also Colinder 399 was also not found. So it could be that our program is just not, you're using a different catalog description than we have. So I did get the request of, what is this, NGC 1976? I probably shouldn't take requests from the stream, or it's incredibly fun to take requests from the stream. Those are the two options. NGC 1976. That is, so I appreciate the suggestion, Qianmu. NGC 1976. That is M42. That is the Orion Nebula. So we can't see that because it's below the horizon. During the winter or during the spring, we are definitely going to be looking at the Orion Nebula. It is absolutely one of the number one things I want to look at. Someone up here mentioned M81 and 82. Those are two irregular galaxies in Ursa Major. Those would be great objects. So let's check, see. Okay, that's a little bit low on the horizon, but I'm kind of optimistic about that. So let's do it. Same deal, I'm going to star hop and first go to Dubhe. Actually, somebody mentioned wanting to look at the double-double, right? So the double-double is Mizar in Ursa Major. So let's just check out that first because it's easy to get to from where I am. Okay, spinning the dome. Looks cloudy, but you can see it. There it is. Let's get the exposure a little better. That's actually really interesting. So this is looking at Mizar. Oh, hold on. I want to tell my computer what we are looking at to make sure the alignment is as good as possible. So Mizar is a very well-known double-double system in Ursa Major. And so what we should actually be looking at right now is 4 stars, 2 pairs of double stars that are in the same system. I think the reason we can't see it is because the atmospheric distortion is so extreme that it is getting in the way of the resolution, meaning that the star images are sort of merging together because the atmosphere is so active. Let me try to reduce the exposure time just to see if we can see this. Yeah, I mean, you might be able to tell that there's 2 stars at the center there, but I really can't. Interesting. It's relatively low in the sky. That might be what this distortion is from. So let's not worry about that and just use this as a pointing star, and let's jump over to M82. I'm not seeing anything that really resembles M82, so I'm going to try to stack a little bit and see if something appears. Do not really see anything. You can see the little dots that are happening in the middle of the screen. Those are not stars. Those are artifacts of the CCD. The CCD is the camera that we're using. Those are pixels that are hot. They are going off even though they're not being hit by any light. So I would say that I don't see any evidence for any of the galaxy in this image. So that's a little disturbing. M82 has a partner. It's called M81. Let's just see what happens if we pop over there. Also not seeing much. I did not really expect to get absolutely nothing. So just bear with me, and I'm going to try to to star hop to something a little bit closer and do another alignment. Yeah, I'm supposed to be on a very bright star, and it is not. It's possible that we have weather. Yes, so sorry, we have incoming weather. There is no visibility in the northern direction. So, things in the north are out for now. What else can we check out? Somebody mentioned, it probably was Justin, that Uranus is actually up now. Uranus is not going to look like much, but I also did not expect to see what we saw in the Martian image. So, it's quite low in the sky, but maybe not too low, so let's try it. Well, actually, it's getting pretty cloudy. It's getting pretty cloudy. I'm not sure how much longer I'm going to be able to do this. No, there's nothing because it is cloudy. I cannot see any stars in that direction. Okay, guys, I think we might be in a little bit of trouble here. Let me turn the lights out and see if I can tell where the clouds are and if I can find an object which is not nearby the clouds. Yeah, the alignment is killing us. That's too bad. Okay, give me a moment to try to fix this. No, I do not like this at all. Okay, guys, I'm not pulling the plug, but I'm going to do a quick reset of our software. The telescope is wandering further and further away from its home base as we get further, as I spend more time away from its home base. So that's not great, and tells me I need to be a little bit more careful with how well we keep it aligned. So I apologize. I don't think. Yeah, Justin, that could have been Uranus. I'm not completely sure that it wasn't, but I couldn't get back to it because the alignment was so off. Okay, so the telescope is realigned. So now let's go back and jump a little bit. We're going to go back and try to find Vega and slew to it. So there we are on Vega. Again, I think someone mentioned the spikes you see are diffraction spikes. So what's happening is there's a mirror inside the front of the telescope which is reflecting the light from the main mirror at the back to the top and then back through the eyepiece, so that the light actually passes through a set of spokes. And when you have overexposed and out of focus stars like that, you get diffraction from the actual
material device that the light is passing through. And obviously the center is black because the star is completely overexposed. But this is definitely Vega, so let's tell the computer that you are indeed looking at Vega, and maybe that will help it as it jumps around the sky. So now I'm going to jump over to Cassiopeia, why not? Sort of, I'm making my way over to Uranus because that is what I want to get to here. Yeah, there it is. Unfortunately, it is also not quite centered in the image. It's pretty frustrating. This is a bright star in Cassiopeia. It's a random one I just picked. It's called Sedar. But now I'm going to tell them that we are pointed at Sedar, see if that helps the recalibration. From here, I should be able to go right to Uranus, so let's try it. Okay, so I can actually see it through the optical telescope, which is attached to the side of the main telescope. So now I just have to figure out what the right settings. Justin says just noise. Unfortunately, I think he might be right. There it is. There it is. But that is just by luck. That is not how I want this to work. Okay, so let's try some exposure. Playing around with, see if we get that looking okay. Yeah, so this is getting a little ridiculous because all the things I'm doing are all electronic, modifying the image because it's electronic, not anything having to do with the actual planet. So let me just sit here and say a few things about Uranus. So Uranus is the third gas giant planet we've looked at tonight. We saw Jupiter and Saturn at the beginning of the night. And maybe as we finish up here, I'll just scan back over to Saturn to take another look. So Uranus is the next to furthest planet away from the Sun. That's obviously Neptune. Pluto, no longer a planet, it's further than that. Uranus is a gas giant. We sort of refer, when I teach students about Uranus and Neptune, I sort of refer to them as the ice giants because they're further away from the Sun than Jupiter and Saturn, and they are the gas giants. Neptune and Uranus are large, maybe like 4 times the size of the Earth. Not giants like Jupiter and Saturn, but they are cold. They are much colder than Jupiter and Saturn, and so they have ice, a lot more ice particles in them, and they also contain loads of methane and ammonia. And actually the color you see here, this bluish color that also Neptune has, is because of the presence of methane in the atmosphere. You can actually take a spectra of these things, meaning you can hold up a prism to them, and you can see methane lines, definitely telling us that there is tons of methane in there. What Justin is saying is that Uranus is twice as far away as Saturn. Yes, that's true. So as you get further and further out away from the Sun, things are more and more spaced out. Close to the Sun, Mars is about 1.5 times further from the Sun that the Earth is. Venus is about 0.7 times closer to the Sun, right, 70%. And so, as you get further away, things get more and more spaced out. So between Saturn and Uranus, it's about a factor of 2 in distance. Uranus is way, way out there. There's only been 2 probes to visit Uranus, Voyager 1 and Voyager 2. I think that's all I really have to say. The other thing about these planets is that they are hydrogen and helium, consisting of hydrogen and helium as a predominant factor, but they don't have the same large-scale magnetic fields that Jupiter and Saturn do. They do have magnetic fields. You can see sort of northern light phenomenon on all these planets, but it's not as ordered as on Jupiter and Saturn because generally Jupiter and Saturn have this metallic hydrogen core which helps drive the magnetic dynamo, and Uranus and Neptune do not have that. I think I don't have much else to say about Uranus. It's got a bunch of moons. None of them are particularly interesting or I have any random facts about. It's got a ring, again, kind of tenuous and thin. Oh, right. Uranus rotates on its side. So the Earth is not quite tilted like this with respect to the plane of the solar system. It's tilted at about 23 degrees. That's what gives us our seasons. As the Earth is tilted towards the Sun, the part that's tilted towards the Sun has more direct sunlight and is in the summer months, and the part that's tilted further away is the Sun's rays hit it at more of an angle. Less direct sun means it's colder. That's the winter months. Halfway in between is obviously the fall. Uranus is tilted completely on its side. So, and Uranus's orbit gives it something like an 80 Earth year long year. So a year on Uranus is 80 Earth years. And a quarter of that time, 20 years, the entire northern hemisphere of Uranus is in summer. Another 20 years, it's in fall because it's hitting on the sort of equator side evenly so that there's about 12 hours of sunlight. I don't know what the rotation speed of Uranus is, but it's half a day of sunlight. Then it spends 20 years with the other pole being in summer and then the northern pole being in winter, and then it becomes this 20-year spring. So Uranus has these dramatic seasonal changes. Justin is yelling at me about Miranda the moon. Sorry, Miranda's a moon of Uranus that I don't know anything about. Please, Justin, tell us in the chat everything you know, all the exciting things about the moon, Miranda. I think that's all I have to say about Uranus. Let's find another. There's still some people in the stream. I am going to quit here soon, but let's just pop around a little bit. There were 1 or 2 other things I wanted to check out to see if they were easy to see. Yeah, M34, there's an open cluster in Perseus. Yeah, there's an open cluster in Perseus, which is pretty nearby where we are. I guess I'll try the jumping off point again and go to the star Almach first.
good. We're reasonably centered. Actually, Almach, that's right, Almach is a double star, so let's see if we can see the colors in Almach here real quick. Okay. I'm going to tell the computer where we are. And then see if I can get this exposure right. Ah, that's pretty. Hold on, just trying to work out what is going on with this star. Yeah, so I think this is pretty interesting. So obviously what we're looking at here is two different colors of star. And you may or may not know, star colors denote a number of different properties about them, most notably their temperature. So blue stars are hotter than red stars. But typically stellar size also influences the brightness of the star. So what we're looking at here is we're looking at one star which is redder and one star which is bluer. The bluer star is definitely hotter, but the red star is brighter. That's a little counterintuitive because you would think that the hotter star would be brighter. In fact, that's normally what we teach in introductory astronomy, is that for stars that are sort of doing their main sequence lifetime thing, blue stars are brighter. And as Justin is saying, OBA, FK, GKM, whatever, that's the stellar sequence, where the OBA stars are bluer, hotter, and brighter, and the GKM stars are redder, dimmer, and cooler, and our sun is right about in the middle at a G-type star. But of course, this looks a little bit backwards, right? We have a red star and a blue star, and what's interesting about this is the red star is apparently brighter than the blue star. Well, the first thing we can say about that is because that star is bigger. So that red star is likely some kind of red giant, which is later in its evolutionary stages. But now, of course, we have a problem here, which is that blue stars are not supposed to live as long as red stars. So that blue star should have gone nova already by the time that we started looking at this system. So likely what's actually going on here is there were two stars. The red star was actually more massive, the one that we're looking at right now, and it started evolving and becoming a red giant, and then it transferred mass onto the blue star, creating a more massive blue star. And so that is likely what has happened. So Justin is saying it's a captured star. That's a possibility, of course. I don't know the details about this stellar system. Maybe we should investigate it a little more, but normally the explanation for a brighter red star and a dimmer blue star is that there's been some mass transfer which has jump-started the lower mass star, which was the blue star before it transferred mass. It's probably the explanation. It could also be a captured star. Captured stars are somewhat unusual, particularly in systems which are so widely separated as this. Captured stars are typically closer together and sometimes merging, but it could be possible. Anyway, I'll stop rambling about that, and let's go on to try to see my actual target here, which was, I forget what it's called, M34? M34.
Okay, well, this is actually what we were supposed to be looking at, so let me just try to center it a little bit. Yeah, well, this is actually right. Unfortunately, this is an open cluster, so I guess it's nice as a comparison image to what we looked at before with the globular cluster. The globular cluster being a tight collection of stars where there's like tens of thousands, hundreds of thousands of stars that are very old. This is an open cluster. It's far fewer stars. So you can see there are a few stars here on the screen. Essentially, it's just too big to fit in one screen. I have to sort of zoom around a little bit to actually be able to look at the entire thing. Sorry, it's really hard to get used to the orientation. It's different every night. So, yeah, you can see there's a few more stars that are appearing as I zoom around. Look at the colors of the stars. They are definitely blue instead of red. Now, the color balance here is a little bit strange, and so it's a little bit difficult to really be convinced that the color are real, but they do seem to be bluer, at least in comparison to the globular we looked at. That's because these stars are much younger. They form together in the same way that globular clusters form, but these are much younger stars. They haven't had time to evolve from being blue stars to being supernova or planetary nebula and leaving behind the red stars. So that's why there's not many. Well, it's not why there's not many stars here. Open clusters form in a different environment than the globular clusters form. The globular clusters formed very billions of years ago, 10, 12 billion years ago, whereas the open clusters are typically 1 to 5 or 6 billion years old, and their stars have not had time to go nova, and they're just forming in a much less dense environment. When the globular clusters formed, the galaxy hadn't formed yet, and there was a whole lot of gas around, lots of available gas for them to form, and so they made these spherical, very dense associations, whereas now there's less gas around because so much is locked up in the globular clusters and other parts of the galaxy that we get systems like this. And of course there are open clusters which are denser than this one. I thought this would be nice because there's often colors you can see, but the field of view of our camera is so small that even this can't really show us the whole thing. Looking at the eyepiece, like I'm going to go and look at the eyepiece right now. I think it's going to be a great image. Can't see it because I don't have the flatter. Yeah, it's actually a very nice association of some red and blue cluster stars that you can sort of see all together. So Justin's saying switch it with the 52 millimeter. Okay, so Justin obviously knows something about telescopes. That's fine. You change eyepieces in a telescope is how you change the field of view and the magnification. So by saying 52 millimeters, he wants to get a very large focal length eyepiece so that it has a very large field of view. He even wants to put some kind of plossel on it, which is a certain kind of optical design. We don't get to do any of that. So what's happening is the camera is acting as the eyepiece. It's a fixed size. It's a fixed zoom size. Now there are ways you can increase the focal length or decrease the focal length of the camera. Due to the telescope design, I can't increase the focal length of the camera at all. So I cannot make the field of view any larger. I can only make the field of view smaller, and that would defeat the purpose in this particular case. So you can't actually get larger images with this kind of camera. Okay, so I think we should just about wrap this up. I didn't get a chance to check out. So I'm near M33. Let me, as a very last thing, just check out M33. First, let's go to a star. I mean, we're near Almach. Let me just pop back to Almach. Cool, there's Almach. And now Justin says M31. Justin is desperate for M31. Okay, I think you'll be disappointed, but let's do it. Okay, so you can see something happening in the center of the image. That is definitely M31. Let me see what I can do about playing with the exposure times. Okay, well, I am seeing something. You can definitely see some kind of core at the center there. So I guess that I'll try to stack, and let's see what we can come up with. Yes, indeed, Justin, I do have another 3 filter I could throw on there, but I think for the sake of time, let's just see what we end up with here. You can see that there's definitely some kind of diffuse core there, and actually you can see the sort of gradations in the galaxy. The galaxy is essentially filling up the entire image. M31 is a huge object. Let me talk a little bit about M31, I guess. So M31 is the Milky Way. Is the Andromeda Galaxy. So in the local group of galaxies, sort of Milky Way and Andromeda are the 2 dominant galaxies, the 2 largest ones. They're sort of like New York and Boston of Northeast, they're sort of the dominant centers. There's lots of other galaxies surrounding us, like M33, M30. There's dozens of smaller galaxies as well as some medium-sized galaxies in our local group. So Andromeda is a spiral galaxy just like ours. It's a little bit larger than ours. It's like 2 million light years away. It's something I tell my students: the Milky Way and Andromeda Galaxy are careening towards each other. They are going to either hit in some kind of head-on or maybe glancing collision in some number of millions of years. You and I will not be here, so it doesn't really matter. And in fact, the stars, although it sounds very dramatic to say these 2 galaxies are going to crash into each other, actually the distances between stars and galaxies are so wide that we individually as stars may not even notice that we are colliding with the galaxy, because the density of stars in our region will get a little bit bigger, but it's not like we're going to be dodging stellar interactions all the time. Now, when the Milky Way and Andromeda collide, there will be a collision of gas clouds, and that will ignite more star formation, and so there could be a lot of sort of more interesting features in our sky in terms of bright glowing clouds at night and things like that, but it won't be a sort of dramatic destruction of anything except for the 2 galaxies, because the galaxies will generally merge into one. So Justin is saying the large and small Magellanic clouds, yes, those are 2 dwarf galaxies orbiting the Milky Way. And yeah, so Justin, I see what you're saying about the dynamic range is probably not that good. That's why you're getting these sort of discrete steps around the center of the of Andromeda Galaxy. Maybe there's a way to change that, but I just don't quite know enough about our camera. Let me take a screenshot, because this is good for us to know that this is what Andromeda looks like, and let me spend just a few minutes before wrapping up to see if I can get the dynamics. Yeah, I think keeping the contrast high. Justin wants to do a Zoom meeting sometime, so you could speak and contribute to the conversation, right? Not opposed to that, kind of a good idea. All I would need to do is screen share to do what I'm doing now, so it would not be hard to make that happen. All right, I'm going to give up. It's getting late. Okay, so I think I'm going to shut the telescope down with this image of Andromeda as the last thing we look at. Everyone who showed up, thanks very much. If you have any comments about how this went, how you thought like this process was, if you would like to do it again, anything at all, please let me know, because I don't really know what people are interested in. I really only want to deliver this stuff if people are interested in it. So please feel free to leave comments. Yeah, sure, say I want to do a Zoom thing. I want to look at these things. Your camera was terrible. I hated looking at you, but I like talking to you, listening to you. Whatever you want to tell me, please tell me. It doesn't mean that I can do it, but I'd like to have these things be more interesting for you guys who are engaged and watching, because that was the entire point of the Mendel Observatory, is to get the public up here as much as possible, which is you guys. So I'm going to stop the stream here real quick. Let me know if you have any comments, and I just really want to thank everyone who is here for being a part of it, and let me know how things go. All right, everyone have a good night. See you next time.